So now I'm not going to go too much in this. When I try to do the predictor, I'm using a sort of standard convolutional neural network setup. There's a lot of other crud in here that I need to make sure it doesn't overfit, but I don't think the details of this are all that relevant for the point, but I just want, in case you want to know exactly what the architecture is, you can ask me afterwards. But there is one point here that I need to make. Okay. That when I do the time offset for my prediction, I have to make sure that that also scales with the system size. Because if I just did a very small time offset, then if I look at those later animations where I zoomed out, it would look static. Nothing would change because compared to that length scale, things are moving slower and slower and slower. So I have to choose the right relationship between time and space so that things move about the same distance in each video. And when I do prediction on these videos, literally I'm just pumping in 3 frames and predicting the 4th. And that's all I'm doing. It's very, very naive. No physics, nothing, just the neural network architecture asking it, hey, what do you think is going to happen next? Then the prediction error has a peak right about the point where the individual particles become indistinguishable. So here, it can tell there's this big object, lots of data about the motion, calculate the velocity very cleanly, figure out where the leading edge is going to be, things like that. And then here, you start to not be able to distinguish different particles from each other. Things get kind of mushy. You can't quite pick out the relevant degrees of freedom. You have to deal with multiple collisions in a single time step. Here it peaks where they become indistinguishable. And then what happens is now, because I have many particles per pixel, I start to get averaging. And that averaging has a certain, if I have n particles in one pixel, then the standard deviation of the pixel intensity is going to go like square root n, assuming that it's additive. So what will happen is that the mean and the variance, essentially the variance collapses down to 0 relative to the mean. So the error that you get just intrinsically from noise goes away as I go to larger and larger scale. Yeah?
A bit of a naive question, but relative to what do you define the indistinguishability of the particles?
Well, in this case, what it is that this peak is about where one particle corresponds to one pixel.
Okay,
yeah.
Sure.
Yep. So that's a very physicsy example. Let's do something more neurological. This is calcium imaging data from a zebrafish brain. Dror pointed me to this data and suggested that we might use the same technique to try to figure out what the natural scale is in these dynamics. And unfortunately, we only have about 170 frames of data, which means it's really easy to overfit the neural network. So the results I'm going to show you next are going to be really, really noisy. So this is what the coarse graining looks like. So here, you can't quite see because of the resolution of the projector, but this is full scale. This is divided by 3. This is divided by 8. You can start to see these pixels are getting blocky at this compressed resolution. Divide by 10, now they're really blocky, and they're also more kind of muted in terms of intensity. I don't have very sharp peaks. And then by 20, they're just kind of uniform. And this is the result. So as I coarse grain by different scales, I have a lot of noise. This thing is overfitting like crazy, unfortunately, and this is about the best we were able to pull out in a week of messing with it. But there is some kind of overall trend. And if I look at the original video, you can see that there are these kind of lumpy activations, right? Like there and things like that. And that length scale, again, crops up right around here. So it's picking out something. It's something you could have seen by eye, but it's interesting that you can actually, in principle, if you had more data, you could get out more nuanced structures. And you could also start to detect causal relationships if you had better predictors. This predictor isn't terribly good. There are some very naive guesses you can make that'll score, just about up here, a 0.9 range. So, if you do better, you'll see more detail.
Sorry, so writing comparison, this prediction error is good or not? So 0.08 warrants up to calculate this prediction error.
This is mean squared error on the image.
Mean squared, okay.
Yeah.
Of each pixel.
Yeah, the mean over the image.
So image is scaled by the 0 to the 1. Yeah, intensity of the image.
Let's see, is that? I think It's scaled before the coarse graining. So the coarse graining does affect the intensity range, and that's partly responsible for the reduction in error at large scale.
Oh, okay. So this is the final state prediction?
This is the next state, the next frame.
The next, how many are you using this time?
So I use 3 frames, predict the 4th. Which,
why is 3?
because if I did 6, then I would really be overfitting, and if I do 1, then I don't get any kind of velocity or any kind of derivatives data. So
you do get it too.
At 2, I would get it. At 3, I can get second derivatives, which I don't know. I mean, I don't have a preconception of whether second derivatives are important to predict zebrafish brain activity, but in some sense, I would love to give it 10, but I don't have enough data. I almost don't have enough data to give it 3, as you can see by the noise here, right? I really want to have 100 times as much data and see what happens. And hopefully, we're going to get it, actually. So, and we can see what happens then.
Right, and that's what you are trying to do here. So, in the previous example of liquid, the components are all almost uniform. Here, each neuron has its own identity and some sensory motor role. And what is your description in the coarse graining?
So, the point I would say is, if this thing just completely fails, then that tells you that it's not coarse grainable, that all of the information from the microscopic scale matters for the macroscopic dynamics. If it doesn't fail, however, despite the fact that the neurons could be individual and have individual roles, it does mean that there is some separation between macroscopic behavior of that brain and the microscopic dynamics. It doesn't tell you immediately that one or the other is important. It doesn't say that you need the macroscopic to predict the behavior of the zebrafish or the microscopic. But it does tell you that they're separable, so that you can actually use a different model to describe each.
So it depends on what kind of macro variable you choose.
Yeah.
And what was the macro variable you chose here?
Just the pixel intensity.
That's coarse grain pixel?
Yeah.
So then in some scale, so just more or less constant random noise.
So eventually what you'll get if you coarse grain down to 1 pixel is you would get things like the EEG rhythms, right? You would eventually get spatially uniform intensities, but you would get things like alpha, beta, gamma kind of rhythms, and you'd be predicting those rhythms based on the past history of those rhythms. And then the question would be, at what scales are those separable from the microscopic dynamics? How does that separation work? So if, for instance, in this graph, there were a big, dip somewhere or a big peak somewhere, that would tell you something interesting is happening at that scale, where when you move across the scale, you're separating between some microscopic relevant thing and some macroscopic relevant thing. And then you could look at that scale and see what happens to be at that scale.
In a more concrete way of saying, probably this kind of analysis can tell you the spatial size of the grain that has a maximum sort of the similarity in terms of functional unit. I don't know about the zebrafish brain, but most of the case, neural system connects to neighboring similar units, right? So I don't know whether this resolution is, the initial resolution is actually lower than that kind of,
I think the initial resolution can pick out individual neurons.
Okay, then maybe if there is a spatial neighborhood that connects or groups functionally similar neurons, then that would probably correspond to the peak prediction error, right?
Yeah.
The minimum.
Yes, and based on this idea, I think how you scale the neuron may be important. Like maybe there are 2 neurons that are highly connected to each other, but they are separate in the space. And if you scale by their correlation and treat it as one cell assembly, so as a next scaling pixel, that may improve.
Yeah, I think there are a lot of ways to improve prediction. Certainly, this is. Oh boy. Okay. So okay. This is not an optimal predictor for the system, right? So you can try a lot of things, but I guess what I want to talk about in the talk is more of the idea of the methodology. So I don't have a specific result about zebrafish here that I'm trying to. I don't have a point about zebrafish, but I have a point that this is something that we could throw together in a week using these ideas, and you can of course do better if you have specific questions you want to look for. This is more of a diagnostic that points you to interesting things to look at, rather than an answer about something in the system. It's a methodology rather than a result. Does that make sense, maybe?
A quick question.
Yeah.
Do you agree that the gain here in coarse graining is negligible? Because going from 1 to any other value, you're only changing things by...
Yeah, as I said, this predictor is really terrible. And part of the reason is because there's not enough data to avoid overfit.
But even if you had like a much less noisy curve, the gain is only like...
But if you have more data, then the gain will be better. Because the overfit is basically preventing you. Like in a previous version of this where I had a slightly different architecture, the neural network was consistently outperformed by the guess that the future is the same as the present. Mm-hmm. So it really, like, it's not just that the noise will go down. The curve will change a lot too if you have better data. But right now we had 170 frames, which is not really enough to train a 6-layer convolutional neural network.
It should be easy to find other data sets online.
Well, Ray is hopefully going to we're going to work with Ray on his data set, which is like 3 hours of video. So that's going to be a lot more than 170 frames. Yeah.
So also, if you can find it, I don't know for how many organisms you have an approximate structure of neural network, the arguments to give. So if you do it on something that you have an approximate connection thing, instead of like doing it on a pixel basis, if you do it on a network basis, that might give you better results.
Well, I mean, as I said, it's a methodology.
Yeah,
so I think there are a ton of things that you can do better than this. This is literally like me doing the stupidest possible thing to show that there's signal, right? Because the first thing to do is get signal and then refine. Right. So yeah, if you're interested in seriously doing it, I think trying to do coarse graining on networks is an interesting thing to pursue. You can do coarse graining on PCA components, for instance. You can do, I mean, there are a lot of different things you could try. Hopefully what this convinces you is that it's worth trying, as opposed to just, never ever looking at coarse graining again in your life. So, all right, so that's coarse graining. But one thing, and this gets back to Farshid's point earlier, is that when you do the exact coarse graining, you find that when it works, usually the way it works is that the coarse grain form is mathematically very similar to the fine grain form. And the only thing that changes is that the parameter values of each term in your equations change. So you have something that looks like it's operating at a certain temperature when you look at it directly, and when you look at it at a different scale, it's as if the temperature were different, but otherwise everything is the same, or something like that. And so that kind of gives you this concept of an effective theory. Because if you have this coarse graining operation where you blur your eyes and you don't see the full reality of what's going on at the most microscopic possible scale, then the consequence of that blur will just be that you measure slightly different parameter values, but the mathematical form will be the same. So in some sense, that microscopic correct theory is equivalent to the theory with different parameter values and different terms at the coarser scale if all you care about is predicting the coarse variables. And that if is important. If you really want to know about the dynamics of a single neuron, you can't get away from studying the single neuron because that's what you want to ask about. But if you want to know about the alpha rhythm or something, you may be able to do all sorts of horrible things with your neuron models, and it may not matter. But this process gives you not just like 2 equivalent theories, but it gives you entire families of equivalent theory. So you can think of this in a sense of like a theory space, where these axes correspond to different terms that you're using to construct your model of the future. It could be different coefficients in the neural network, or if you have something with a Hamiltonian, it could be different terms in the Hamiltonian, or if you have some kind of dynamical process where you have different kind of contributions to how things change in time, it would be the terms that characterize those changes. And you'd have an axis for each such term that could be relevant. And then within this space, these curves correspond to applying successive coarse grainings. So as you go to larger and larger scale, the curves all go somewhere. And this is a fixed point, which in dynamical systems theory, it's a point where if you're sitting at that point and you apply sort of the evolution operator, in this case it's a transformation scale, but it could be in time, then you don't move. And in this particular case, this fixed point is an attractor, in that trajectories from nearby converge on the point rather than going away from the point. So if I'm not on the point, I move closer to it. If I'm on the point, I don't go anywhere. So, yeah.
Could you list some example of effective theory, the same equation applied to different scales?
Yeah, so this is a very physics example. I apologize for it, but it's the one that immediately springs to mind. The Ising model is the one that basically everyone uses to map this out because it's easy. It's the easiest one to do it with. In the Ising model, you have a magnetic field that's externally applied, but you also have the interactions between neighboring. In the Ising model, you have these things that are spins. They can be up or down. And things that are up make their neighbors also want to be up. And things that are down make their neighbors also want to be down. And the external field makes everything want to point the same way as it, either up or down. So you can say, how strong is the interaction between the neighbors? And that would be one axis. So that's, say, J is the symbol used for it in physics. And then the magnetic field is the second parameter, which is called H in physics. And what you find is that when you are at a certain value of H and J, and you scale the system, you do the coarse graining, then you'll move either going to J equals 0 or to J equals infinity. And so that choice of whether you're on one side or the other of the decision gives you whether something is magnetic or not, whether something will actually, stick to a ferromagnetic surface and things like that. So that's an example. And all of those things, there are actually a whole bunch of other potential axes that exist, because in the Ising model, you only have nearest neighbor interactions. But if you have, say, 3-body interactions or second nearest neighbor interactions or all of these different terms, it turns out that as you go up in scale space, they all collapse down to 0. So it says that you don't actually need to worry about them at all when you go to the infinite limit. You can actually forget about these kind of localized but extended terms because they all turn into just a change of the value of the local term. And that's sort of a way in which you have this effective theory emerge. It tells you, I don't have to care about a spin that's 8 guys away, and I don't have to integrate around my local neighborhood because it won't change the infinite. If all you care about is the infinite scale properties, it won't change them.
Nicholas?
Yeah.
Is it okay just to mention that the central limit theorem is the simplest possible example of this? Because a lot of people know that they use Gaussian fluctuation.
Okay, that's a good one. Yeah,
but they often don't realize why they get away with it in a very complicated way.
Yeah. So,
but that is just a comparison of the level of coarse graining. In the highest scale, the distribution is not Gaussian anymore.
Correct.
Yeah. That's why I was saying if you care about a fine scale question, you need the fine scale description. But if you care about something on a scale that's different than the fine scale you have access to, then you can usually get away with making errors. So if I care about a fluid flowing in a river, I can make errors. That river can be made of water or honey or alcohol. And the consequence of that is just changing the viscosity and changing the density. I don't have to worry about the fact that glucose has a certain shape until I get to very long molecules, and then I fall into a different entire class of fluids, of non-Newtonian fluids. But then that becomes kind of, well, you'll see. So this is not agreeing with me today. Okay, so this is supposed to be model 1, since I'm not going to get it to cooperate. So the idea is at the fine scale, water and honey, and glycerol, alcohol, whatever. And then when I zoom out, everything goes to the same point, and I just get fluid dynamics.